derivative,
integrals,
differentials.
Hello guys, today's lesson is taught by Alan and Ray. So right now we're learning chapter 14.7. This unit is a continuation of the previous one, 14.6. But the difference is that in 14.6 we learn triple integration in 3 dimensions, and the application of it, all of that is in rectangular coordinates. And as we learned before, there are different ways to represent the same function or different functions, because sometimes it's easier to integrate some of the special functions in their unique forms. Right now we're going to learn about cylindrical coordinates. Just a review of cylindrical coordinates. So in rectangular you have x, y, and z. And in cylindrical, pretty much, x equals to r cosine theta, y equals to r sine theta, and z is just z. And there's still 3 directions of integration, but instead of standardized x, y, z, you integrate to angle and then a function, as you can learn in the textbook. First is the angle on the ground, so to speak, like xy plane, and then another angle of elevation, and then the integration to the function. So the standardized formed this one, you can say triple integration of x, y, z dv derivative volume. The theta 1 to theta 2 first, and then g1 of theta to g2 of theta. So this is the underground elevation, and then h1 r cosine theta, r sine theta, and this is the integration to function. Theta, r sine theta. This is a standard form, not finished yet, because you still got to integrate the function. As I told you, in the last chapter, integrating x, y, z, and right now I pretty much plug it in x, y, z here, and then d. Oops, 1 second. That, and then also you gotta times the r, as you see in previous chapters. We're just gonna do r. We're integrating in respect to r. We're doing dz, dr, d theta. Here's an example of triple integration with cylindrical coordinates. For example, now I have equation f squared plus y squared plus d squared equals 4. So that's a sphere, you can imagine. Find the volume of solid region Q cut from the sphere by the cylinder r equals 2 sine theta. And you can see the graph in your textbook. That's better than my drawing. First of all, you want to see from what value are you integrating to. Then in this one, we learned that x equals to r cosine theta, y equals to r sine theta. So if you understand the big rule, you can understand that r squared actually equals to x squared plus y squared. The original function becomes r squared plus z squared equals 4. And then the bound of z, you can see z is order or equal to 4 minus r squared greater or equal to negative 4 minus r squared. We need this because now we know in what range we can integrate z. And the volume is actually very easy, so we can see why it's a lot more effective than rectangular, because cylindrical, especially with like a symmetrical shape, like a sphere, so easy to integrate. So we want to integrate from 0 to pi first, and then we want to integrate for r from 0 to 2 sine theta, and then we want to integrate the function, the range of z, so from negative 4 minus r squared to 4 minus r squared. And it's not that scary. And then you just pretty much integrate R. It's the only thing you need. And then look at the order. But now you're integrating Z, so it's dZ first. And then you're integrating R. R is 0 to 2 sine, and then dr. Last but not least, d theta. And that's pretty much all you need. But let me draw the line better. So then I could solve this by integrating step by step. I'll do one step, and this is integrate this. That. But I'm not gonna finish the calculation for you because you can see that in the textbook and you should do it by yourself. But eventually this should give you a number because you're integrating everything. At the very end, I think you get approximately 9.644. And that's how you integrate by triple integration by cylindrical coordinates. Wow, good job guys. I finished 1/2. We'll learn about rectangular, cylindrical, and the next one, the last one in your book is the spherical coordinates. If you remember, we have worked with all of these coordinates before this chapter and unit. So same thing, x, y, z. X equals to rho sine. I don't know what that sine. I don't know what this is called. Cosine theta. And rho sine this thing and sine theta. Z is actually different from z. And then again, this is a triple integration. So in triple integration, you're integrating with 3 directions. In rectangular, you're integrating x, y, z coordinates, and that's the easiest. Not the easiest one, the most straightforward one. And then cylindrical, you're integrating in terms of angle and elevation. That's a little different. And then again, in spherical, so first you're integrating an angle on the xy plane, then you're measuring an elevation, an angle from the equation to the xy plane, and then eventually z is the equation, like the height it reaches, and you can represent x, y, z by these 3 equations. And the standardized form, imagine x, y, z. I draw x, y, z here. And then if you learn well in the last one, the theta 1 to theta 2 is first. And then this angle, elevation, second. And then you're integrating rho, which is pretty much the equation and the distance you're integrating. And the f, as I told you, in the past we roll x, y, z, and then you substitute that. So you're writing f of rho sine this angle cosine theta, and rho sine this thing sine theta, rho cosine thing. And then you're integrating, like this cylindrical, I always integrate r. Now integrate rho square sine this thing. I have 3 d. First of all, d rho, and then d this angle, then d theta, which makes sense. Triple integration by spherical coordinates. Okay, let's now do a practice problem with spherical coordinates. So if you pay attention to how I represent x, y, z, you realize it's pretty cool. Rho squared is actually just equals to x squared plus y squared plus z squared. And that's kind of similar to r squared equals to x squared plus y squared, but this is cooler because it includes x, y, and z. But here's the problem. Look at the example 4 in your textbook. Find the volume of solid region Q bounded below by the upper nap of the cone. D squared equals to x squared plus y squared. I don't know what that word means, but I know this is a boundary. And above the sphere, x squared plus y squared plus z squared equals 9. Okay, I'm showing the figure. So, as I showed you right here, you can get rho squared equals to 9, and you get rho equals 3. That's critically important because you have to integrate from 0 to 3 with respect to rho. And then furthermore, the intersect, okay, if we set, okay, so we're trying to integrate this between these two curves. We want to see where they intersect. So we're understanding that x squared plus y squared plus z squared equals plus d squared. Right? This pretty much lovely. D equals 3 over root 2. Well, if you understand that, then the question is pretty straightforward, because if d equals to rho cosine this angle, and you know what rho is. So actually, if you use inverse cosine, you understand this angle by 4. So pretty much what we're doing here is we're trying to find the range that we're going to integrate in each direction. We already find that rho is 3, so we're going to integrate 0 to 3. And find that for this angle, we're going to integrate from 0 to here. Last but not least, we're going to try to find theta. Actually, we don't need to find theta because understand we're integrating the whole circle. The theta is actually just 2 pi. Well, not 2 pi, but between 0 and 2 pi. Okay, now we integrate. So, volume. The theta first. There's 2 pi, 0 to pi over 4, and 0 to 3. And rho squared sine angle d rho d and d theta. Okay, isn't that straightforward? And this is in example 4. I'll do one step, did last time, but I'm not gonna finish integration for you guys. Literally on your book. You should practice integrating by doing it yourself too. Straightforward. And eventually you're gonna get a value 3.563. So that's spherical. So pretty much you see we're doing the same thing here. We're trying to integrate for some volume, which is very popular type of problem with this chapter. That you're integrating a 3-dimensional thing. So however you want to represent it, some shapes are easier to integrate than others for certain coordinates. So pick the coordinates that fit and solve the problem efficiently. Thanks for watching, guys.
And we'll attach a note sheet under the video, and I think it can help you to review this section and just like a math cheat sheet, you know what I mean.